Welcome to Chelsea. This is where I have my home and my telescopes, including my beloved 12.5-inch reflector. In this very special program, we're going to look at 400 years of the telescope in astronomy. It's a marvelous story, and over the years, we've been to some of the world's great observatories.
100 years ago, the world's largest telescope was the great reflector set up by the 3rd Earl of Ross at Birr Castle in Ireland. The telescope was completed in 1845, and we're going to talk about it in this evening's Sky at Night. I am standing on top of one of the most remarkable telescopes in the world. We're at Kitt Peak in Arizona. Mount Wilson is one of the peaks overlooking the city of Los Angeles. It's 5,700 feet high, nothing special, and outwardly there's nothing to mark it out. La Palma is now becoming famous in another direction. It's here that one of the world's great observatories is being set up. The great 28-inch telescope is coming home where it belongs, at the old Royal Observatory in Greenwich Park.
Sun-soaked palms and temperatures in the mid-80s. But there's another angle to Hawaii too. A region of thin air, icy cold, and winds up to 150 miles an hour. And that's where I am now, on the top of Mauna Kea, nearly 14,000 feet above sea level.
Its great strength lay in its light-gathering power, which was very much greater than any other telescope made up to that time. Remember, what you want to do in astronomy is to see very faint things. And to see very faint things, you need to collect as much light as you can get. And the bigger the mirror, well, the more light you can collect. And this is where the big Ross mirror came in.
Even with the naked eye, you can carry out a great deal of work in astronomy. But of course, the telescope makes all the difference. So, who made the first telescopes, and who first turned them skyward? Most people say Galileo. Well, I talked to one of our regular guests, Dr. Allan Chapman, who has other ideas.
All that we can say is on the 2nd of October, 1608, a German living in Holland, a place called Middelburg, a man called Hans Lippershey, presented a petition to the States General, the Dutch government, for a device that made distant objects appear close using a pair of lenses. The thing is, he didn't get his petition or his claim because 2 other Dutchmen immediately leapt in and said, we've got the device as well. So actually we don't know. The key thing is, though, what happens is this is the first use of the telescope in the world. Now, because he didn't get a patent claim, very quickly, these devices went on sale across Europe. They were on sale in Frankfurt, and Paris, and various other places by the end of 1608. Now, an Englishman called Thomas Harriot acquired one from somewhere. He called it his Dutch trunk, and what the original device was a pair of lenses in a tube. An object glass and an eyepiece. The object glass has to be thicker on both sides, it has to be convex. The eyepiece has to be narrower in the middle, a concave. Put them both in the right positions and boom, suddenly, distant objects appear close. Now what the Dutch were finding is looking at, let's say, ships or distant buildings. The Dutch, of course, at that time were at war with Spain. There's a war of liberation against Spain. Useful strategic device. But Harriot uses them scientifically. On the 26th of July, 1609, he looked at the 5-day moon.
So Harriot was the first telescopic astronomer?
Without any doubt, or the first one on written record. Now, what his telescope would look like is probably something like this. I made this replica some years ago, which is the same as the 2 lenses, object glass at this end, eyepiece there, and this magnifies about 20 times. When I look at the moon with this, I can see the main craters. 1 or 2 known points, but certainly the Mare Nectaris, the Mare Tranquillitatis, Mare Crisium, and 1 or 2 features. And then, all of a sudden, the realization is the telescope shows you things you can't see without it. And over the course of about a year and a half, Harriot makes a series of maps. Now, it's true, by the summer of 1610, he would have had Galileo's observations, which had been published in Venice in March 1610, and we know were on sale in England in June of that year. But also, too, Harriot is making better drawings of the moon than anything in Galileo. And then he makes an undated map, but certainly around 1610-11, of the whole moon. And that is a stunningly beautiful map.
It is.
It has the seas, it has lots of prominent craters. He had no idea what he was looking at. He didn't quite know what the whole moon was made of. But as a piece of cartography, it was superb.
These early telescopes were refractors. Then, of course, we come to reflectors.
And this little telescope we have over here, this brass instrument, unknown from the Science Museum, is in fact of the Gregorian pattern. And this is how a Gregorian worked. And very kindly, the Science Museum has provided us with a cutaway instrument. And because these are nearly 200 years old, we handle them with white gloves so that acids from our fingers won't actually affect the metal. And what happens, you have a parabolic mirror down here. The light comes in, hits that mirror, is reflected back up to a second mirror, is then reflected back down through a hole in the main mirror and to an eyepiece. Once you've got the reflecting system, you are then able to see bigger, brighter images because it was easier to make big mirrors than it was to make big lenses. What William Herschel called space penetrating power. And they came to realize very early on, when you make a more powerful telescope and a more powerful telescope, you see more stars, more stars, more stars. Is the universe infinite? Does it go on forever? The telescope is the first instrument that shows us that we can see things beyond our normal five senses. And you think the telescope, the microscope, the barometer, in more recent times, photography, digital imaging, TV. I suggest the telescope is the first. It's the first that shows us we can go beyond normal vision. And in that respect, it's transformative in so many ways.
This is my main telescope, my 15-inch reflector. Well, here in Chelsea, conditions are as good as they are anywhere in England, but of course they're not perfect, and the world's big observatories have to be very carefully sighted. One of these is Kitty Peak in Arizona, and Chris went there.
Deep in the Arizona desert, 40 miles away from the bright lights of Tucson, is a world-famous collection of telescopes. Astronomers first came here more than 50 years ago for the clear skies and the dry air. From a distance, you can still see the sparkle of the silver and white domes gleaming in the relentless sunshine. Welcome to Kitt Peak, America's national observatory. With 25 or so domes scattered across the mountaintop, this is the largest collection of professional telescopes anywhere on the planet. The largest of the more than 25 telescopes here can be used by astronomers from any university or any country. This is the home of astronomy for all. Down in Tucson is the National Optical Astronomical Observatory, which is in charge of Kitt Peak. It shares a campus with the University of Arizona, and as students walk to class, I talked to Doug Isabel about the early days on Kitt Peak. So how long have there been telescopes on Kitt Peak?
Well, it was 50 years ago that Kitt Peak was selected as the site of the U.S. National Observatory. After a search all across the continental United States, about 150 different sites were looked at, and Kitt Peak was selected due to its very, very clear, dry weather, its overall good climate, its dark skies, and also it was close to practical things like a university, like an airport where the scientists could fly in from their universities, which were largely in the east, which is why Kitt Peak was founded in the first place, to give these eastern scientists and midwestern scientists a place to do their astronomy with nice dark skies.
So what was on the mountain before the astronomers arrived?
We're actually on the land of the Tohono Nation, a Native American nation separate from the United States in many respects, and we're a tenant there, and we're honored to be on their land. Basically, we have a long-term lease through the National Science Foundation with the Tohono Nation. On the mountain, the telescopes are being prepared for the night. In charge of the oldest large telescope on the mountain, the 2.1 meter, is Dr. Howard Bond. When the telescope was new, he would have been assisted by an operator, but now he has to do everything himself. Times have changed. It was with this telescope that astronomers were first able to probe the fingerprints of hydrogen in distant galaxies, helping them piece together the history of the universe. Today, Howard is using the telescope to follow up on observations made using the Hubble Space Telescope.
Tonight, I'm working on a program that's related to the Hubble Space Telescope. So with Hubble, we're measuring the distances to stars using the parallax effect. Those measurements are relative to surrounding background stars. And to get an absolute true distance, we need to make an estimate of how far away those background stars are. To do that, we measure their brightnesses and colors, which is a perfect thing for a ground-based telescope, like the 2.1 meters telescope that you see behind me here.
These are relatively local. It's surprising we don't know the distance well already. Why do we need to know so accurately how far away these stars are?
Well, the problem is we use these Cepheid variable stars, which are very bright stars. And we know that their brightness depends on the period of variation. But the question is setting the 0 point. And there aren't any Cepheids that are close enough to the Earth to have their parallaxes measured very accurately with ground-based telescopes. In fact, the nearest Cepheid variable is the North Star, Polaris, which in fact I'll be observing tonight if the weather stays clear.
Hasn't Polaris been behaving oddly recently?
Yes, its range of brightness has been going down. In fact, some people predicted it would stop being a variable star, but it's kind of bottomed out and it still is varying at a low level.
And is this your first night on the telescope?
This is my third night. No, it's my fourth night. I've already had 3 nights.
So you've been living nocturnally?
Yeah, trying to, yes.
If the skies stay clear, Howard will look at about 24 stars tonight to measure their brightness. But this isn't the only telescope which will be working tonight. This is the Malin telescope. When it was built, the second largest optical telescope anywhere in the world, and still the largest on Kitt Peak. Its giant 4-meter mirror is used for everything from looking at the edge of the solar system to studying distant galaxies. The designers of the Malin telescope in the 1960s gave it a radical look. The dome sits 92 feet above the ground in an attempt to keep it clear of turbulent air. As with all telescopes, it's kept up to date with new cameras and instruments, but the control room still has something of the feel of the inside of a battleship. Tonight, Dr. Kimberly Herman is preparing to take a close look at some nearby galaxies.
When we look at spiral galaxies, the rotation curves gives us the total mass of the spiral galaxy. But how much of that mass is in the bulge, is in the disk, and is in the dark matter halo? That's what we want to know. By studying planetary nebulae, we can look at the motions in and out of the plane of the galaxy to determine what the disk mass in the galaxy.
Why look there? Why are we interested in the outer regions?
There are some very strange things going on in the outer regions. There seems to be more mass out there than we would expect, and so I'm trying to see how much light is out there, if there's really enough light out there to explain the mass that I'm finding.
Kitt Peak was born from a noble vision that good ideas win you time on telescopes. It was and is astronomy for all. These historical telescopes may not often grab the headlines today. They serve as workhorses rather than show ponies. But it's the meticulous work done here, night after night, decade after decade, that slowly reveals what our universe is like.
Kitt Peak remains in the forefront, and there are other great telescopes too. There's in Hawaii and in the Atacama Desert. All of these were built in the latter part of the 20th century. It's an impressive instrument. As with most large reflectors, the tube is a skeleton, and the mounting is a massive horseshoe. The main mirror is 154 inches in diameter, or 3.9 meters if you prefer metric, and that puts it in the world's top 6. When the question of an observatory on the top of Mauna Kea was first discussed, I'm sure there must have been plenty of raised eyebrows. The difficulties were so obvious: inaccessibility, and above all, the effect of altitude on the observers. But the challenge was taken up, and the observatory is an unqualified success. When you're building a big telescope, I suppose about 50% of the problems are engineering, and the other 50% are optical. And obviously, the main component optically is the big mirror of the telescope. And this rather strange-looking construction is the illuminizing chamber, inside which the mirror is kept until it's ready to be put into the telescope. It is being brought out now especially for us, and I think we are some of the first people to see it like this. When I began the Sky at Night series in 1957, the biggest telescope in the world was the 200-inch at Mount Palomar in California. But of course, the early 20th century was the period of the first great reflectors and great observatories. With me, Professor Richard Ellis of Oxford, we shall welcome back to the programme.
Thank you.
But that was a great period, wasn't it?
It's been a fantastic century of discovery in astronomy, and the large telescopes have without question contributed an enormous amount. They've really shaped our view of the universe. If one imagines the expansion of the universe, discovered with a 100-inch telescope, and then understanding stellar evolution with the 200-inch, and now the Keck and the European large telescopes pushing the frontiers to the most distant galaxies that we can see.
There have been various telescopes that have marked new developments, and one of these was the 100-inch at Mount Wilson, for a long time the most powerful in the world and in a class of its own.
Yes, from the period in the early 20s until after the Second World War, the 100-inch was the largest telescope in the world, and probably its biggest discovery was the expansion of the universe.
By Hubble, of course.
By Edwin Hubble himself. And of course there were earlier work that had shown that galaxies were moving away from us, but Hubble showed that the distance to a galaxy is correlated with the speed with which it's moving away from us.
And you had to use the 100-inch for that. No other telescope would do it.
That's right. And of course this means that the universe had a beginning, and so that really is a profound discovery, perhaps the most significant discovery of the 20th century.
Hale, who masterminded the 100-inch, he wasn't satisfied.
He was an amazing man, George Ellery Hale. He founded Caltech, he founded the American Astronomical Society, and he was a relentless raiser of money for large telescopes.
There were many problems to be faced, financial and technical.
The 200-inch was an amazing challenge. Making the mirror was probably the biggest challenge of all. There were several attempts to cast the mirror. In the end, of course, they were successful. And that mirror is still in use, celebrating 60th anniversary of world-beating science this year. And it's still in use doing frontier work. And that's a good example of how a telescope is a lasting achievement. Telescopes are not stagnant things. They can be updated with new instruments, and the 200-inch is testimony to that.
What do you think are the major advances by British technology?
Firstly, the Anglo-Australian telescope,
Yes,
a fantastic project, 3.9-metre telescope in Coonabarabran in Australia. Its probably biggest achievement was the Galaxy Redshift Survey, the so-called 2-degree field redshift survey. So this is a huge step forward in our understanding of how much mass there is in the universe, the nature of dark matter, and the distribution of galaxies of various kinds, spirals, ellipticals, on large scales. The William Herschel telescope is on a better site. It is a magnificent technical achievement, has fantastic instruments, including faint object spectrographs, which were able to look at gravitationally lensed galaxies. And this was an era when Hubble was launched, and so there was a good synergy between the William Herschel telescope and the Hubble Space Telescope. And then probably I'm a big fan of UCERT. This is a very cost-effective telescope, very cheap on the summit of Mauna Kea, which is now doing a big, deep infrared sky survey. But it has achieved a lot in infrared astronomy, and I would argue that British astronomy in the infrared was in the world lead for a long period when UCERT was the largest infrared telescope in the world.
Now, come on to the VLT. How much are we involved in that?
Britain is a full member of the European Southern Observatory for many years now, and most of the British astronomers are doing their cutting-edge work on the ESO VLT. This is 4 8-metre telescopes, tremendous versatility, some of the best instruments in the world, particularly for spectroscopy in the infrared and in the optical region.
What are the greatest achievements of the Keck, do you think?
I would select 3. Firstly, the discovery of the most distant galaxies up to redshifts of 7 and beyond, where we're looking back, believe me, 90 to 95% of the way back to the Big Bang. So that's really one area, I think, where Keck has been supremely successful, simply because it's got fast spectrographs and its 10-metre aperture. Then I would select gamma-ray bursts. These are very energetic explosions. We didn't know whether they were, oh, heaven forbid, we didn't even know whether they were in the solar system, in the Milky Way, or in the distant universe.
Luckily they're not.
They're not. They're not in the solar system. They're a long way away. And so these are tremendously energetic bursts of activity when 2 black holes or a black hole and a neutron star merge. And then finally, the accelerating universe, the use of supernovae as standard candles to trace the history of the expansion.
Are you happy about that?
Well, I'm involved, Patrick, so yes, I'm very, very excited, and I think it's a remarkable result. And of course it was found independently by 2 teams.
So the expansion is accelerating?
The expansion is accelerating. And
why?
We don't know why. And we give a label of dark energy to it, but of course, who knows what that means? And so there's a lot of enthusiasm now in the astronomy community to try to get to the bottom of this. But there's a good achievement from the Keck telescope.
We said for a long time the Ross telescope was superb, then the 100-inch was, then the 200-inch. Would you say now the Keck telescope is ahead of any other?
It's hard to say. The Subaru 8-meter telescope and the ESO VLT and the Gemini observatories, all of them are doing frontier work. Keck had a wonderful advantage by being slightly larger. 10 meters over 8 meters does matter.
Yeah, it does.
Yeah, it's 10 squared over 8 squared. And of course, Keck had a head start because it was on the scene earlier. So, you know, much of the early work was creamed off by the Keck telescope, and that gave Californian astronomers an advantage.
The essential part of the reflector is its main mirror. Everything depends on how good the mirror is. Chris has been over in Arizona seeing how 21st century mirrors are made.
Tucson in Arizona is a busy university town. It's home, among the cacti, to the scientists who ran NASA's Phoenix lander on Mars, to astronomers who use telescopes like those on Kitt Peak, and to the Arizona Wildcats. You'd expect any American university worth its salt to have a pretty impressive football stadium, but this one's special. Underneath me is the world's most advanced telescope mirror laboratory. The heart of any telescope is its mirror, and as far as mirrors go, size definitely matters. The more light they collect, the better the image is. But size comes at a cost. Big mirrors are heavy, requiring lots of support as they're swung around the sky. Here at the Steward Mirror Lab, they have a novel way to make big mirrors that are a fraction of the weight. Dr. Peter Weinger told me how.
What's behind us is the casting for what is the world's largest piece of glass that will go into a telescope called the Large Synoptic Survey Telescope, LSST.
What stage is this mirror at, and what's happened to it already?
We start out with a set of hexagonal columns.
You can see those still in the
that are roughly a meter in height, and there are some 1,700 of these columns. They're aluminous silica, and they simply serve as a mold to create a honeycomb structure, and we install something in the vicinity of 23 metric tons of glass on top of the hexagonal columns, and it takes about 1 million watts of power to heat the glass 24/7. And at the end of a week, the glass is liquid, and it seeps between the hexagonal columns and produces a honeycomb structure with a layer of glass on the bottom and another layer on the top and vertical columns in between.
So what's this structure on top of the mirror?
These circular discs and all of the steelwork above it are basically all part of a distributed lifting device that will enable us to lift the glass right from the front surface. So we have something called RTV silicone rubber.
That's just bathroom sealant,
yes,
right?
And it works very well. And then the steel work above it is simply a means of distributing weight over the whole 23 tons.
LSST is due to look at the sky for the first time in what, 2014 currently?
2014, 2015, something in that.
And yet it's only 2008. Does it really take that long to make a mirror?
Typically it takes about 3.5 to 4 years to produce a single mirror. We typically in the Mirror Lab have several mirrors in various stages of casting, grinding, polishing, and so forth.
Earlier this year, the Sky at Night filmed up the road at the Large Binocular Telescope, or LBT. Its 2 mirrors were both made in the Steward Mirror Lab. The LBT is itself the prototype for a truly enormous beast called the Giant Magellan Telescope. It will have not 2, but 7 mirrors, and is due for completion in 2017. It may seem a long way away now, but here in Tucson, one of the mirrors destined for that telescope is already nearly complete. The team here are using the latest technology to produce their mirrors. It's incredibly high tech, but the motivation is the same as it's always been. Astronomers want bigger and better telescopes to look further into the universe. Roger Angel is the mastermind behind the design of these mirrors, drawing inspiration from the long line of scientific mirror makers stretching back through the ages.
This is a mixture of very old technology that would be very familiar to Newton and Galileo and very new technology that allows us to go so big and so on. And the part that would be instantly recognized by those guys is the fact that when we polish the glass, the actual what contacts the glass is pitch, and that's exactly what Galileo and Newton used. So after 400 years, right, we're still using the same material that actually rubs the glass that they used so long ago. And what happens is that if you put a plate with pitch on the bottom on the glass and wait for a bit, after a few days it will fit exactly the glass. Now if you rub that plate around on the glass, if it's got bumps in it, then as you move the pitch around, all the high bumps, both on the pitch and on the glass, will get worn away by the polishing compound, and the motion keeps finding the high spots. So Galileo was able to make a lens whose surface is accurate to a millionth of an inch, right? People have gone back, looked at Galileo's lenses, they're fabulously accurate. So here's a time where there were no machine tools, nothing of any accuracy, and yet this process, because the pitch smooths out and flows out and you move it over the glass, makes this hugely accurate surface.
Well, you can build mirrors up to 8.4 meters in diameter. Is that a maximum size?
Well, when we wrote the first paper suggesting these mirrors, it was about 30 years ago, we set 8 meters as the size of the freeway.
Right.
Because we can make a mirror perhaps bigger than this in this room, but if you need to get it to the highest mountaintop and it's got to go on a boat, in particular on the freeway. So when these mirrors leave, we block the entire one direction of the freeway. So all the traffic is held up until the truck gets off the road. So this is about the limit of transportation.
It's awe-inspiring to watch these giant mirrors rolling off the production line, and it makes my mouth water to imagine what they'll see as they light the way forward for astronomy.
We use telescopes to look at the sky, but what about the sun? Can we use telescopes there? The answer is yes. Galileo did, and did it sensibly. But you've got to be careful. The sun is dangerous. So here's Pete Lawrence to explain how to observe the sun safely.
When you think of a telescope, you probably think of one used for nighttime observing, looking at the stars. But of course, telescopes can also be used during the daytime as well. And the sun presents a fantastic opportunity to see a star in close-up. So how do you look at the sun with a telescope? Well, there are various ways of doing it safely, because the sun gives out a lot of light, a lot of heat, a lot of energy. If you don't do it correctly, you may damage your equipment, or worst of all, you may damage your eyesight. So let's have a look at a few ways of actually looking at the sun. One of these is to use projection. And to do this, you basically point the telescope at the sun, let the sunlight come through the telescope and onto a piece of white paper or white card. When that happens, you actually have an image of the sun appearing on the card, and that's an extremely safe way to look at our nearest star. But there is a danger, and you must be aware that if you have a finder on your telescope, this too acts like a little projection telescope. So the best thing to do is to remove the finder completely, and then there's no danger of any heat build-up at the back end of the finder. Not all telescopes are suitable for looking at the sun like that. Reflecting telescopes, for example, or Schmidt-Cassegrain telescopes aren't, because there's a heat build-up close to the secondary mirror, and if the secondary mirror gets hot, it can actually shatter and break and then fall down onto the primary. So the best type of telescope is undoubtedly a refracting telescope, a lens-based telescope to project the sun. Another way to look at the sun safely, and this way encompasses other types of telescope, reflectors and Schmidt-Cassegrains and refractors, is to use special astrosolar film. It's a piece of aluminized mylar that fits basically over the front of the telescope. You buy it in sheets A4 size, which are about £15 a go, make your own filter, and then make sure you can attach it securely to the front of the telescope. If the wind blows and blows the filter off, then you could be in real trouble. So it has to be extremely firmly fixed. It's also a good idea to check the filter before you put it on by holding it up to the sun and making sure there aren't any holes in it which could let light directly through. Now, when you look at the sun using a filter like this, you're looking at it in what's called white light. If you want to see the sun in a different light, more exotic light, then we have to use a speciality filter. And I have a hydrogen alpha telescope here. It's a relatively small, relatively inexpensive one, about £500 or so. And this will filter the sun so that we block out most of the light, but we're just looking at it in the light of hydrogen alpha. And this allows us to see burning, glowing hydrogen on and around the sun. Using a filter like this, we can see prominences leaping off the side of the sun and dark snaking filaments edging their way across the sun. If you have a normal telescope like this, and you wanted to convert it to be a hydrogen alpha telescope, you can do that as well. You have to buy a speciality filter, such as this, which fits on the front of the telescope, and that converts the telescope into a hydrogen alpha telescope. And you can look through it using a special blocking filter which goes in at this end, and together they allow you to view through the telescope directly at the sun and see all these wonderful exotic hydrogen alpha features. So whatever method you use to look at the sun, do it safely and enjoy the wonderful views afforded by our nearest star.
Well, these are ground-based telescopes, but now let's turn to space. And that means the Hubble Space Telescope, launched in 1990. And a little while ago, I talked to two people deeply concerned, Professor Martin Barstow and astronaut Professor Jeff Hoffman, who's been to the telescope.
3, 2, 1, and liftoff of the Space Shuttle Discovery with the Hubble Space Telescope, our window on the universe.
At 1 day, 43 minutes mission elapsed time, this is Hubble Telescope Control, Greenbelt. Otherwise, everything going very smoothly here at the Space Telescope Control Center.
Congratulations on a super mission, and the world is looking forward to reaping the benefits of your good work over the next 15 years.
The Hubble Space Telescope, still going strong. Jeff, may I come to you first? You've been to Hubble. Must be a great experience.
You know, it's 15 years since our initial rescue repair mission to Hubble. Hubble has been such an incredible success over all that time that I think many people forget what a disaster it was right after launch when we discovered the optical problem, the despair, the outrage that the astronomical community, the public at large, the Congress in the United States felt. NASA was really in a crisis, and I was fortunate enough to have been on the mission which actually saved Hubble.
Did you know exactly what the trouble was?
Well, it turns out it was a spherical aberration of the main mirror, which is a very, very common error in amateur telescope making.
By a tiny amount.
The amount of extra glass that they removed from the outside of the mirror was about 1 micron. That's about 1/50th the diameter of an average human hair. Very tiny, but it shows the precision with which Hubble operates, that just that tiny amount made it impossible to get good focus out of the Hubble optics.
When you got to Hubble, what was your actual role?
Our actual mission followed several years of painstaking analysis by astronomers and optical engineers where they figured out what the problem was, and then they developed some very clever ways of installing corrective optics. That was our job, was to install those corrective optics as well as correct several other problems, because several things had failed on Hubble. We had to replace some of the gyroscopes, we had to replace some of the fuses, some electronic boxes, but the most important thing was to get the optics fixed.
And that meant spacewalking, of course.
Well, one of the remarkable things about Hubble was that it was designed from the very beginning to be serviceable by spacewalking astronauts. That meant that you can actually operate Hubble much in the same way that we operate ground-based telescopes, where you build a telescope, they have a mirror, the mirror is then fixed. But as years go by and detector technology improves, you continually upgrade the detectors that you put at the focal point. This had never been possible with telescopes in space before, and Hubble was unique because of that ability. And we use that capability to remove and install instruments with high precision to actually be able to install the corrective optics.
You're essentially an X-ray astronomer, aren't you?
Well, that's what I started out in my early career, but once I went to NASA, I realized I wasn't there to do research, and I have to say that to have been able to fix Hubble and make it available once again for the astronomical community, I probably made more of a contribution to astronomy than I would have had I continued to do research.
Well, Jeff, it must be a magnificent experience to go to Hubble. And
I was very lucky. I mean, as an astronomer and an astronaut, to put my hands on Hubble in its working environment, which is in space, was the thrill of a lifetime. It doesn't get any better than that.
All right, stop. Let's just look at the labyrinth field. My side looks good. Yeah, mine's beautiful. Okay.
Well, Martin, the next repair mission is now being actively planned. What's it going to do, actually?
Well, there are several really important things that we have to do on the next mission. The gyros have to be replaced again. We're always replacing gyros because they fail fairly frequently. They're relatively fragile things. I now know more about gyros than I ever wanted to know. But for me, more excitingly, is the installation of two new instruments, the Cosmic Origin Spectrograph, which is an ultraviolet spectrograph, and the third Wide Field camera 3, which will replace the Wide Field Planetary Camera 2 that Jeff installed all those years ago.
I'll be looking forward to seeing that when they bring it back on the ground. Get my hands back on it.
Yes.
I'm sure you will, yes.
But I think the other important elements are actually not new instruments, but repairs to old instruments. Both the Space Telescope Imaging Spectrograph and the Advanced Camera for Surveys suffered failures. They're very important instruments still, and there are plans to repair both those, which we hope will be successful, and they will be among the most challenging parts of the mission. And last but not least is the repair to the command and data handling system, which failed just before the planned launch for the servicing mission last October. Without that, nothing else will work effectively, because we don't have any redundancy at the moment in this particular system, and that must be replaced to make sure that we have the planned lifetime. This is probably going to be the most challenging servicing mission ever undertaken. The number of things that they have to do and the limited number of spacewalks they have to fit them all in is going to make it very difficult. There isn't really any room for any problems.
We have come to expect 100% success for this mission, but that doesn't mean that it comes easy. You can't ever relax when you're planning for these missions. And as Martin said, some of the things that they're going to try to do on this mission have never been attempted before. They're actually going to take apart an electronic box and make a repair on the board level, pull out an electronics board and put a new one in. I mean, this was never imagined when Hubble was designed. It's just extraordinary.
Yeah, there's a nice analogy about the ACS repair, the Advanced Camera for Surveys. It's a bit like doing a heart bypass. Yeah. They're actually going to take up a new piece of electronics and strap it across the old one to try and bypass the failed area.
How much lifetime do you think you've got?
We would hope and expect that it will go on till at least 2015, and a big aim at the moment is to actually plan for an overlap with the James Webb Space Telescope, so that we have what is billed as Hubble's successor, although those of us in UV and optical astronomy don't really agree so much. But we'll have those in space at the same time, working together, which will be immensely powerful.
Hubble went up in 1990. It's still there. It's pioneered space telescopes. It's been an outstanding success.
Absolutely, I agree wholeheartedly. We were thinking earlier on about all the amazing things that it's done. The monitoring of the explosion on V838 Monocerotis, the fantastic images of the light echo as that shockwave has spread out and the light reflecting back from the surrounding gas has successively come back from different parts of the material that's been thrown off. One of my other highlights was the spectroscopy of an extrasolar planet, which is a remarkable piece of science that you could never have anticipated Hubble would have been able to do when it was launched.
Jeff, what's your favourite Hubble picture?
I would have to say that the ability to pick out the supernova far away in the universe that's led us to appreciate the fact that the expansion of the universe is actually accelerating. It was completely unexpected and has changed our view of cosmology completely. I mean, Hubble has done so many things, but if I had to pick just one, I think that's what it would have to be.
Well, certainly Hubble is still in a class of its own. Been a magnificent success, and thank you both for coming to join us.
Patrick,
Yeah.
it's always a
It's
pleasure.
always a pleasure, Patrick.
Thank you so much. Even though Hubble's taken marvellous pictures, everyone's got their own particular favourites. Mine happens to be of Mars, but others may have different ideas. And we've been asking our contributors to select their favourite pictures, and here are the results.
My favourite Hubble image is of Abell 2218. Abell is a cluster catalogue, clusters are large groups of galaxies in the universe. And this for me was the most spectacular demonstration of gravitational lensing. So you have this big galaxy in the middle, and around it you have all these little tiny arcs, and each one of those arcs is a distant galaxy that has been perturbed as the light comes from behind the cluster. And for me, you needed the resolution of a space telescope to see these fine details.
You're seeing behind me my favorite Hubble image. It's the Hubble Ultra Deep Field. It's the deepest picture ever taken of the universe. What happened was the Hubble Space Telescope opened its shutter and took a 3-month-long exposure of a dark patch of sky that had essentially nothing in it. And instead of seeing nothing, the Hubble Space Telescope saw 10,000 galaxies.
My favorite Hubble image is the one that shows Saturn, not only the rings of Saturn, but the aurora, both at the North and the South Pole. I have a rather soft spot for Saturn because I have an instrument on the Cassini spacecraft. But the reason I like the auroral image is you can actually see it standing up off the North Pole, and it shows you different colours. It shows you red and white, and so you can see helium and hydrogen in the atmosphere. So I think it's spectacular.
I actually worked on the instruments, or one of the instruments for the Hubble, and that was the faint object camera. And I think the image that I remember was the image of Pluto, and for the first time showed it as more than just a mere dot. And it became, at least to me, it seemed like a real object with character.
I think the most amazing results from Hubble have come when it's given us glimpses of solar systems forming around other stars. Look deep into the heart of the Orion Nebula with the Hubble Space Telescope, and you see not only stars, but these strange objects. These are Propolis, dusty disks silhouetted against the bright background gas, and from these disks, planets will form. Or look at this disk around the bright star Fomalhaut. Look into the disk, and you see a planet, formed and moving around its parent star. Our first glimpse of another world.
My favourite Hubble image is the wide field view of the Whirlpool Galaxy M51. But what I think is amazing is that even though this galaxy is 37 million light years away, Hubble reveals all those wonderful pink starburst regions along the spiral arms, and you can actually see the way the smaller galaxy is distorting the structure of the spiral arms of the larger neighbour. And that's why I think it is an amazing image.
It would have to be the pillars of creation. That to me it symbolised the first of the Hubble images that started to come through that just gave this completely new vision of the cosmos. And it was just completely fascinating to think that in these three sort of sticks of candy floss, this is where stars are forming. This was what you could do with Hubble.
Well, now let's come back to Earth. What will telescopes of the future look like? Well, here's a model for them, the Hobby Ebony telescope in Texas. And Chris went there.
I set off this morning from El Paso in the far southwest of Texas, driving alongside the Mexican border. The road is on a gentle incline because my final destination is the Davies mountain range, which at 10,000 feet offers some of the darkest skies anywhere in the continental United States. The McDonald Observatory has been perched on top of Mount Locke and Mount Fawkes for the past 76 years and is now run by the University of Texas. The two oldest telescopes here are the Otto Struve, built in 1933, and the Harlan J. Smith telescope, which dates from 1966. Their newest companion, which I've travelled to see, is the Ebony telescope. Astronomers are greedy. We always want bigger telescopes to give us more light so we can see fainter objects. The silver dome behind me contains a telescope that's not only large, but also rather special. The design of the Ebony telescope, which was completed in 1997, is revolutionary. It's still the third largest astronomical mirror in the world, but it was built at a fraction of the cost of a normal telescope of this size, and the reason is its mount. On the next mountain over, director David Lambert is operating one of the older telescopes. Its heavy mirror needs a strong mount so it can be supported properly when it's pointed at the sky. The larger the mirror, the more difficult and the more costly this becomes. Solving these problems is not only difficult, it's expensive. But here at the Ebony telescope, they've come up with a radical, cheaper solution. The giant mirror stays fixed and the sky turns above it.
This is made up of 91 identical segments about 1 meter across. The goal is, of course, to make a very large mirror, in this case 11 meters across. Can you imagine making an 11-meter piece of glass? It's heavy and it's very difficult to transport and maneuver. When this was finished in '97, it was the third largest in the world.
How do you keep the segments in position?
At the beginning of the night, we point the telescope to a tall tower outside, and there's a laser up in the tall tower which fires down at the 91 mirrors, and then there's a computer program and adjustments behind each mirror that allow us to align the 91 images on top of each other.
Up above the giant mirror, a secondary moves to follow objects in the sky for a short while. It works well, but compromise comes at a price. Not all of the sky is visible to the telescope.
The telescope was designed from the very beginning to have a structure containing the optics that is fixed at an angle, in this case, of 35 degrees.
So this mirror always stays at this angle?
It always stays at this angle. That was a cost saving. We saved probably 80% of the cost of making the same size telescope fully steerable.
You don't need this huge mount that can
swing around. We don't need the huge mount. We don't need the motors, the engineering. The cost, of course, is that we only can ever observe objects that are in a ring 35 degrees off the vertical. That ring, because of the motion of the tracker, has a width which is about plus or minus 8 degrees. So over the course of a year, 70% of the sky passes through the ring.
How long can you observe a single object for?
That depends on where the telescope is pointing. If we're looking due south, it's about 45 minutes. If we're looking due north, it approaches 2 to 3 hours.
The other beautiful tweak to the telescope design is in the way it rotates.
The telescope, during an observation, is resting on 4 of these feet, which are resting on this concrete pillar. After an observation, we want to point to a different point, north, south, east, and west. So the telescope 100-ton structure, as you can see, is getting now an inch off this concrete.
And supported just by?
It's supported by 8 of these airbags, 20 pounds per square inch.
Wow.
Like a little hovercraft. In fact, if you put your hand here, you can feel the air coming out.
Yes, you really can.
So the telescope during the night is operated by the telescope operator from the control room, moves round this concrete pillar. The computer tells the telescope structure when it's at the right compass point or azimuth.
Yep.
And then the air is cut off and the telescope comes back down, this foot comes back down.
So how quickly can you move from one object to another? So that's always crucial.
Well, the design was just a few minutes, so we don't lose very much time.
The telescope specialises not in taking images, but in using an instrument called a spectrograph. This splits the light from objects into their constituent colours, telling us what stars and other objects are made of. David took me to the observatory's new visitors centre, which uses light from the sun to explain exactly what the spectrograph does.
We're producing an image of the sun, and the image is projected from a telescope on the roof of the building. From the image of the sun, the little slot of light is fed back to what we call a diffraction grating. Think of it as a prism. It spreads the light out into a spectrum, a rainbow of colours, and that's what you see projected.
And as well as the rainbow from violet through to red, I can see dark lines in the spectrum. They're important.
Yes, we call those Fraunhofer lines or absorption lines, and they are produced by atoms of different chemical elements in the atmosphere of the sun absorbing some of the light. So from those lines we can trace out which elements are present, which are not, and determine also the amount of those elements, things like the temperature and pressure and the velocity flows in the atmosphere of the sun.
With the power of the Hobby Ebely's giant mirror behind them, astronomers have used a spectrograph to study stars sprinkled throughout the galaxy. So what can the Hobby Ebely telescope tell us about stars in our galaxy?
Well, because of the large aperture, the telescope can look at quite faint stars, and we have the high-resolution spectrograph in the basement, and so one can determine whether there's a correlation between the metal content, as we say in astronomy, and the motions of the stars, and ultimately lead to clues as to how the galaxy was assembled. In a star like the Sun, the metals make up less than 2% of the mass of the star.
And they come from previous generations of stars?
They come from previous generations of stars by nuclear reactions inside the hot interiors of stars. There are then processes, usually explosions, that get those elements out into the interstellar medium, and new stars form containing these metals or contaminants.
So I know you've looked for some of the metal poor stars, right, those which are relatively pristine. Why are they special?
Because they were formed early on. What the real search right now is to find the most metal poor stars. There have been recent discoveries where the metal content is 1 part in 10 to the 5th what it is in the Sun.
That's 1 part in 100,000?
Correct. And those stars possibly formed from gas that was contaminated only by the very first generation of stars to form from the Big Bang. And they were very special stars because they only contained hydrogen and helium.
I've been to many observatories around the world, but I've never seen anything quite like the Hobby Ebely telescope. It may only be able to see a fraction of the sky, but the ingenuity of its design is hard to beat. Every telescope, every observatory has its own story, from the new technology of the Hobby Ebely behind me to the amazing legacy of Kitt Peak. With a new generation of giant telescopes already under construction, I'm sure the most amazing stories are still to be written.
And that takes us on to the future. Richard, where do you think the future lies?
Well, the future does indeed lie with segmented mirror telescopes. There are 3 groups now planning larger telescopes than the Hobby Ebely and the Keck telescopes, and all of them involve segmented mirrors. So starting with the 30-meter telescope, this is a collaboration between Caltech, the University of California, Canada and Japan, and the segments themselves, there will be 490 of them. So a telescope of that aperture is really very, very powerful, and one of the driving forces is to study galaxies at the very edge of the universe, perhaps the first generation of galaxies to switch on when the universe is only 3 or 4% of its present age.
What about the atmosphere?
Of course, we have to get rid of the atmosphere because it blurs the signal. Fortunately, adaptive optics has made tremendous progress over the last 10 years. It's quite challenging to correct for the blurring over a big aperture, like a 30-meter diameter.
How exactly do you do it?
Well, the way it works is you shine a sodium laser beam into the sky along the direction of the object you're interested in observing, and this reflects off sodium atoms high in the atmosphere.
Which are there already?
Which are there already, and they create a spot of light, which is effectively an artificial star. We monitor the signal from that artificial star and correct for the blurring using a deformable mirror, a small mirror made of many little components, each of which can be moved independently.
How many corrections per second?
It's several corrections per second, and these deformable mirrors have several hundred individual components. So the technology is quite demanding, but the progress has been so great that we're now optimistic can be applied to these larger telescopes. So the other telescopes are the European extremely large telescope. This is a 42-metre telescope, and that is really a balance between, obviously, the amount of money that ESO thinks it can raise for a telescope of this aperture, and, of course, the desire to have even better performance than the 30-metre telescope. And then the final project, which is quite exciting, is the Giant Magellan Telescope. So it's an exciting time, driven, of course, by fundamental scientific questions, such as imaging extrasolar planets, looking at the earliest objects in the universe, and, of course, studying cosmology and dark matter, and the fundamental questions of the origin of life and the nature of the universe that we live in.
Well, Richard, why the quest for even bigger telescopes?
It never ends, Patrick. George Ellery Hale once said, light is falling on the Earth from all over the sky, and all we can do is collect the bit that lands on 100 inches across. He was driven to build bigger and bigger telescopes to learn more about the universe. The quest never ends, and the technology enables us to do it. It's a very exciting future.
Richard, thank you very much.
Thank you.
We began the series way back in April 1957, and look how much has happened since then.
Despite all the electronics, visual photography is still used for some branches of research. David Malin, who came to Siding Spring as a photographer, spends his observing time in a cage at the prime focus. The official name of the observatory is El Observatorio del Roque de los Muchachos. I'm afraid my Spanish accent isn't very good, but here are Los Muchachos, the two boys. I'm sure there is a local legend about them, but no one seems to know what it is.
It's coming out, yes, there is the moon, I can see it for the moment. No, it's gone again.
It's gone, however...
Absolutely infuriating, there's nothing one can do.
The heart of any telescope is its mirror. And here we have the 4-metre or 158-inch mirror of the main telescope on Cerro Tololo. It really is enormous. It's 2 foot thick, and it weighs 15 tons.
We're clouded out here.
There is some kind of... Look, wait a minute, there's some kind of a break over there, can you see it?
I can't see anything in it, though.
No.
This very neat and efficient-looking dome contains a 10-inch reflecting telescope. And just to make sure that we all know where we are, the latitude and longitude is given on the door.
The Royal Greenwich Observatory gave it to me in order to pinpoint my position if I sent in any observations.
Do you find that the dome's easy to turn?
Yes, once you get it going, Patrick, it's quite easy. Look here, you see. Just you to have a try.
Yes. Well, that's pretty easy. There's no difficulty there.
Of course, there's still a lot of drifting cloud up there, and we just can't tell whether it's going to be obscured at the critical moment. Of course, you won't see Vega looking large, because no telescope yet built will show a star.
It's gone,
except point right. Is it gone? Oh, no.
Just as I got it on the crosswires, it blacked right out.
How absolutely typical. There's nothing we can do about it.
The next morning, there was a 70 mph gale. And when I arrived at Herstmonceux, the wind was really tremendous. And it was just as much as I could do to open the door to get inside the great dome. Astronomy is unlike anything else, and one can give as much or as little time to it as one wants to do. Yes. You can still get a tremendous amount of enjoyment, and if you do useful work as well, so much the better. Good night. Good night. Good night. Good night. And so, from Brighton, where the sky is now completely overcast, good night.
Good night.
Well, I think you'll agree, it's a wonderful story. We've come so far in the last 400 years, from the tiny telescopes of Galileo's time through to the huge telescopes now. We can look back into the depth of the universe. It's a story well worth telling. I hope you've enjoyed our look back at the history of the telescope.
Telescope Night continues here on BBC4 tonight. The story of the Great Hubble Telescope is next, followed at 10 by a brand new Storyville, where a new telescope tries to explain the formation of the galaxies. And at 11:20, Time Shift enters the nighttime world of the amateur astronomer.